Hi everyone, hope everyone's doing well. So this is our second talk with a new kind of format. The idea is to talk about some big ideas in physics, current physics. First one was by Ken van Tilburg, as Lars mentioned, and that was on dark matter, so it involves particle physics and astrophysics. And today we're moving into the area of hard condensed matter physics. We will be recording this talk, but not the question and answer part, which will follow the talk. So don't worry, you can ask any question you want. It's not going to go down permanently in history. So the format will be about a 20-minute talk, followed by this question and answer period. There'll be plenty of time for your questions. So we're very lucky today to have Anna Keselman as our speaker and guest. She did her undergraduate work at Tel-Aviv University, so Israel, and her MS and PhD at Weizmann Institute, both very distinguished universities in Israel. And she has also worked in that period as an algorithms developer for an aerial imaging company. You can read about it in the bio attached to the announcement for this talk. For the last 3 years, she's been here in Santa Barbara as a postdoctoral scholar, first at Station Q, which is on our campus right by Cone Hall, a research group in quantum computing, funded by Microsoft, but on our campus. And now she's a postdoc with the KITP. So thanks very much, Anna, for agreeing to take up this challenge. And I'll pass it to you for Stronger Together, Safer Apart in the Quantum World.
Great. Yeah, thank you for the introduction. It's a pleasure to try and give this talk. Okay, so basically I want to tell you today about electrons. So if you think of all the elementary particles that we know that form the standard model, and maybe also keep in mind, following Ken's talk last week, that there might be other particles that we don't know about yet. You might wonder, what's so interesting about this one specific particle, which is the electron, and don't we already know everything there is to know about it? So yes, we probably know everything about a single electron, but kind of the question I would like to address today is, and the question that a lot of the condensed matter physicists are thinking about every day, is what happens when there are many electrons in the system. And that is a very different question, of course, and a very difficult one. And we know some of the answers to it, but certainly not all of them. So let me still start from a single electron. The word electron is actually the Greek word for amber. And this is because ancient Greeks noticed that amber attracted small objects when rubbed with fur, and therefore started calling similar materials like amberish or electric. So nowadays we know that this behavior is just due to the transfer of elementary particles, which we call the electrons. And electrons have charge, and therefore they strongly repel each other. There's a strong Coulomb repulsion between them. And they also have spin, which is kind of their intrinsic angular momentum. And this property, you can think of it as making the electrons act as tiny magnets. So, as I already mentioned, I guess, what makes studying electronic systems really exciting, at least for me, is that these are systems where there are many electrons. And when I say many, it's not just 10 or 100, right? It's 10 to the 20. So there are, if I think of a cubic centimeter of metal, then the number of electrons in it is more than the number of stars in the universe. And Phil Anderson, who was an exceptional physicist and a Nobel laureate, and he had numerous contributions to condensed matter physics, In this paper that is titled "More is Different," really put forward this idea and kind of tried to explain to the scientific community in general the idea of emergent behavior. So this is behavior that can be understood, or that cannot be understood simply from the properties of the individual constituents, but rather that emerges when the different parts of the system interact as a whole. And just quoting from the paper, it says that the behavior of large and complex aggregates of elementary particles, it turns out, is not to be understood in terms of a simple extrapolation of the properties of few particles. Instead, at each level of complexity, entirely new properties appear. And so in this talk, I would like to mention a few examples where such new emergent properties appear in electronic systems. And of course, I won't go into too many details, but I just kind of want to mention different examples and show the rich variety of behaviors it can give and why they're interesting. And in particular, focus on phenomena that can occur in systems that are cooled down to very low temperatures, where quantum mechanical effects also become very important. And some of those examples are very well known, even outside the scientific community, while others will be still in the level of theoretical predictions. And we are all kind of eager to see whether they can or will be observed in real materials. So let me start from the well-known examples. Of course, one of the most known examples is superconductivity. And in this case, we know that electrons form pairs, which are called Cooper pairs. And the collective behavior of these pairs allows for a vanishing electric resistivity in a material. And as a result, for the flow of kind of dissipationless current. Another known example is magnetism, so ferromagnetism. So in this case, the electrons, which are pinned to the atomic lattice, like to align their spin. So when all the spins are aligned, there is some total net magnetization in the system. And so this example have not just been observed in experiments, in the labs, but have by now led to tremendous technological breakthroughs, starting from MRI scanners and high-speed trains where superconductors are used, and hard disks where ferromagnets are used to store information on our computers. And these are just a few famous examples, but there are many more. So now let me mention maybe a few examples which are less known, but maybe even more interesting. In particular, I'd like to mention a few things that can happen when we restrict the motion of the electrons to a plane. And we can do that by basically kind of trapping the electrons using electrostatic potentials. So in particular, I want to think of different things that can happen when we, in addition, apply a magnetic field perpendicular to this plane, so pointing along this direction. So we know that charges in the magnetic field move in circular orbits, and the size of the orbit depends on the magnitude of the magnetic field. And so it turns out that at certain ratios of the magnetic field to the density of the electrons, a tight packing of such orbits can form. Okay, so something like this. The electrons kind of stay localized, going in circles, and you can really think of this as a kind of a stay-at-home order for the electrons. They're just forced to stay in place and go in circles. Now, another an interesting thing that happens in the system is that while the electrons in the bulk are kind of forced to stay localized, there are very robust modes of propagation along the edge of the system. So in analogy, you can think of this as the frontline workers. And they're even robust in sense, they're very robust in the sense that even when there is disorder in the system or impurities, it won't disrupt their propagation. Now we can ask what happens when this kind of state-home order is lifted, and we can do that, for example, by changing the magnetic field so that the orbits are not so tightly packed, and the electrons kind of have more freedom to move around. So of course, it's kind of harder for them to know what exactly to do, but then it makes them come up with even more interesting solutions. So it turns out that at some ratios of the number of electrons to the magnetic field, electrons can even appear to have a fractional charge. For example, 1/3 or 1/5 or other fractions of the basic elementary charge. And this is, of course, very surprising because we know that electrons are elementary particles and their charge is quantized. So how does it happen that we can measure objects which are kind of originating in these electrons that have a charge which is a fraction of the electronic charge? So I won't explain how this happens, but I'll just say that this has been measured in a number of experiments over the last about 15 years. And so indeed verified that this kind of theoretical prediction indeed occurs. So another interesting thing that happens in the systems, or another interesting property of this kind of fractionalized electrons, is related to the wave nature of this particle. So you can recall that in quantum mechanics, all particles also behave like waves. And you can really think of waves on the surface of the water for the analogy. And waves, when they're overlapping or superposing, they can form interference patterns where the intensity is slightly larger or slightly lower in an oscillatory fashion, like the ones you can see here. And so it turns out this fractionalized electrons that appear in these two-dimensional systems, they can have very different interference patterns. The origin for this is in the fact that when kind of the corresponding, when the particles, the fractionalized particles are exchanged or go around each other, their corresponding waves acquire some phase. So their wave is slightly modified. And this phase shift, which is correspond to this jumps in the pattern that you can see along the lines here, is a very unique feature. And so you could ask, like, why should we care about some phase shifts that the wave acquires? But in fact, this property stands behind the fact that the systems are one of the proposed platforms for quantum computation. And in this case, the operations are really on this quantum computer would be performed by interchanging or moving around this fractionalized electrons. And I should mention that while the fact that the electrons or the effective particles in the system can have fractional charge has been observed experimentally and tested already a while back, a clear observation of this fractional statistics, where you can see this kind of phase jumps in the wave properties of the particles, is a very recent and exciting result from a group in Purdue. So maybe another example I wanted to mention, or a set of examples maybe, is related to what happens in systems, where again the electrons are so densely packed that they're pinned to the lattice, to the atoms on the lattice. So this is kind of similar to what happens in the ferromagnets. But now imagine the situation where kind of the microscopic interactions between these electrons are such that spins on or electrons on neighboring lattice sites or neighboring atoms prefer to align their spins in opposite directions. So they want the spins to be anti-aligned, like here. You see, so these neighbors have the spins in opposite directions. Then in some cases, so depending on lattice, they can actually, they all can arrange themselves like on a square lattice. So you see that it works, and they all know what to do. So this is an ordering which is called an anti-ferromagnetic ordering, which is pretty similar to ferromagnets, but slightly different. While on in other cases, on generally on more complicated lattices, maybe the simplest case for this is the triangle lattice, the spins are frustrated, so they don't really know what to do. So you can see that if these two spins are anti-aligned, so that they are pointing in opposite directions, this third spin that is their neighbor wouldn't know what to do to be happy, right? Because if it anti-aligns with this one, it will be aligned with the other one. In the case of the triangle lattice, they actually managed to figure out some compromise. But in more complicated lattices, this kind of frustration results in the fact that even when we cool the system down to very, very low temperatures, the spins don't form any magnetic ordering. And such systems are called, we call them spin liquids. There are a lot of different types of spin liquids with very different emergent behaviors. But at least in some of these, even though the electrons themselves cannot move, there are some emergent spin excitations. So some effective particles that carry the spin of the electron that can move around. And you can ask, well, how will we know that something is moving around? So if, since the electrons are pinned to the lattice, there is no flow of any electric current. But what we can do, or try to do, is to measure thermal transport, so transport of heat in the system. And this emergent particles that carry the spin will carry some heat. So there are, in fact, a few experimental systems or few materials where such behavior has been at least claimed to be observed. So these are some measurements of thermal transport that indicate behavior, which is a signature of a spin liquid, of this kind of spin liquids. Those are results from a group in Japan. Unfortunately, however, this experiments have not been this behavior has not been reproduced yet in other groups who attempted it. So we're still waiting to see whether this spin liquid behavior can be observed in this or other materials. But for now, this stays on the level of more theoretical prediction. So I hope that I convinced you that the collective behavior of electrons can give rise to a very diverse and rich set of phenomena, and some of which we could already probe in experiments, less or more recently. But some of the properties we're still trying to understand, so there's definitely still a lot of questions, like what kind of behavior can emerge. So I gave you a few examples, but maybe there are a lot more. In what systems, what is required for it on the microscopic level, can such systems be engineered? And of course, how can we observe or experimentally test this behavior and the emergent behavior? Yeah, so there are definitely a lot of questions we still want to answer, but maybe I'll try to answer some of the questions you might have now. Thank you.
Thanks very much. Let's clap for Emma. virtually. That was amazing, and I asked her to make it like 15 minutes, and she really met that challenge, and I can tell you it is very difficult.